Good afternoon and welcome to this third session on the short course on uh, archaeological and heritage studies using geospatial technology. The third session will focus on use of geospatial techniques and methods for documentation and damage detection of built heritage. In the previous two sessions, we had an overview of all the technology and methods that were available. And the second session dealt with ground-based techniques, particularly focusing on terrestrial laser scanner and close-range photogrammetry. Another ground-based technique will be dealt with in the next coming session on microwave data analysis for heritage studies and archaeological applications. There, GPR, ground penetrating radar, will be dealt with. Today, we will look at how to use all these techniques and methods, how to acquire data for documentation, and after documentation, how to do damage detection. I am Dr. Hina Pandey. I will be dealing with the first part, that is the digital documentation, and my colleague Dr. Poonam Tiwari will be following it up with the damage detection section. Now, we've already gone through all this introduction. However, just to summarize again quickly, we know now that cultural heritage refers to the physical and cultural assets, both tangible and non-tangible, which have been passed on to us by our previous generations. These historical structures are one of the most significant elements of cultural heritage. Therefore, in this session, we focus on built heritage. And these reflect history, lifestyle, traditions of a country and society at large. Cultural heritage is threatened by various factors. That is why documentation becomes so important. And finally, after documentation, we can do damage assessment of these built heritage structures. So the various factors which threaten cultural heritage or built heritage especially are natural hazards, vandalism, anthropological activities like development of cities, etc., and natural aging, since these are all structures which have been there for a long period of time, right from the ancient times they have been there, so they have been exposed to the elements, and due to natural aging, they are affected and damaged. The built heritage refers to structures like monuments. So these have suffered significant damage, and especially in a country like India, which has such diversity and so many conditions prevailing, that it is majorly our large population also. So here it is majorly due to human activity and population pressure. So anthropological activities become very important in this damage assessment part. So proper mapping, damage detection, and digital documentation of these cultural heritage sites or archaeological assets thus becomes very essential for their preservation and protection. So approaches for comprehensive digital documentation need to be developed so that these cultural heritage sites are properly monitored and managed. Now, we can do this by employing techniques and instruments which are capable of providing multidimensional information in a quick and easy manner. We discussed these methods and techniques, what data to use, what techniques in image processing, etc., and how to utilize that in the previous two sections. With the applications of these data and techniques focusing on documentation and on damage detection, these two sections will be discussed today. Now, once documentation has been done, this will enable effective monitoring and conservation of the monuments and heritage sites. Comprehensive documentation of a structure has to be able to understand. It is done to be so that we are able to understand its condition better. So data may be in the form of detailed descriptions or engineering drawings, photographs, 3D models, or archival historical records. We can club all these together, use complementary information from each, and in a synergistic manner, we can do a very comprehensive digital documentation. It is an added advantage if the documentation is in the digital format. So storage, analysis, and dissemination of this information becomes infinitely easier as compared to the classical forms of or the traditional methods of documentation, in which we only had hard copy, paper related documents. So digitizing these documents will be helpful to us and will give us an edge in managing and monitoring the heritage structures and sites. Now, looking at all these points, 3D digital documentation is and would be a very effective way of monitoring structures over a long period of time. So, geospatial techniques and methods play a very important role in this documentation of heritage structures and archaeological monuments. Development of new sensors, data capturing technologies and methods, processing approaches, all of these together contribute very significantly to the 3D documentation, conservation, and digital representation or visualization of these structures and sites. Methods that we can use in recording and documentation of the heritage buildings, since we are focusing mainly on built heritage structures here, could range from surveying techniques, digital photogrammetry, terrestrial laser scanning, ground penetrating radar, spaceborne data, satellite data, which could be from the optical wavelengths, it could be hyperspectral data, microwave data, thermal data, and anything that suits us for the particular application. Data from UAV platforms, etc. Anything, or club everything together, use complementary information from each technique and use it in a synergistic manner, combined format. The state-of-art approach for 3D documentation and modeling of large and complex sites use and integrate multiple sensors and technologies. So we could use photogrammetry, scanning, topographic surveying, spaceborne data, microwave, GPR data, etc., all together to do a very comprehensive documentation, detailed documentation of various aspects of the heritage site. Integration of these technologies would enable exploitation of the individual techniques and would also compensate for their limitations. So, for example, laser scanning is an active technique and it is range data, so we only have point data and not image data automatically. So combining it with image related data, we could enhance the limitation, the objectives of the individual techniques. Capturing data at different geometrical levels of detail will also become possible, and this can be done with more accurate, precisely, and a complete 3D geometrical model with interpretation and representation can be achieved. Multi-scale data through multiple sensors, integration of these will provide the best 3D results, the most comprehensive results in terms of geometric detail and visualization. So a very complete and augmented, comprehensive 3D digital documentation would be possible if the integration of all these available technologies is effectively done, efficiently done. So just to recapitulate, these are the techniques and remote sensing data that are available. The passive sensors give us optical data in optical wavelengths or infrared wavelengths. Data could be multispectral or hyperspectral, could be in the thermal wavelength. The active sensors will give us microwave data, could have laser data, altimetric data. The platforms on which these sensors are installed could be satellite-based, air-based aircraft aerial data, unmanned aerial vehicles, that is UAV-based, or it could be ground-based data. We could also use multi-temporal data for doing change analysis. So we could monitor the structure over a period of time at various dates and see how it has changed, or how the anthropological activities are affecting the structure, or what imprints these are leaving on the landscape around it. So the laser data, both aerial or UAV or terrestrial laser data, this can be used to refine the spectral results, the spectral information that we get from optical or multispectral and hyperspectral data by including surface morphology, that is the elevation information. It gives us very high level of detailed information about the height. So this can be integrated. And either a digital elevation model, which includes all elevated surfaces, or a digital elevation model which has only ground elevation, can be derived from this data. Also taking the difference of pre-event and correlating it, and the pre and post-event correlation, the areas affected by the damage can be identified. We will show you examples of these in the forthcoming presentation. Now, I will begin with 3D digital documentation. Now, the entire workflow has been arranged in 3 parts: documentation, damage assessment, and then reconstruction of the heritage sites. So first, the data acquisition techniques and integration of multi-source and multi-platform data to enable improved 3D documentation of the heritage site. Then in the documentation section, architectural primitives have been extracted. So some sample primitives have been extracted and put into a digital library so that if these are broken or if they are lost, then we can reconstruct them based on these samples that are available in the primitive library. And digital blueprinting of the heritage sites has also been attempted. Then in the next section, damage assessment using image processing techniques by using both point cloud data or height data and image data has been done. And finally, once the damage has been detected, techniques for reconstruction or virtual reconstruction have been proposed. So the entire procedural workflow tentatively could be that you acquire data. So here it could also have EO data, Earth observation data here. Then pre-processing of the data is done. From both of these, 3D point clouds are obtained. Image data could also be obtained, and data is integrated. So this forms a very crucial part of the workflow, how to integrate data from multiple sources and to best possibly augment the final 3D model. Once the data has been integrated and the 3D model has been generated, you can extract architectural primitives based on samples that are available. Then damage detection and assessment studies could be done. Using the primitives, a 3D blueprint could be generated for the heritage site or the monument. Reconstruction and virtual relocations could be done of artifacts, of entire buildings, etc. These were also showcased yesterday in yesterday's presentation. And by combining all the information together with ancillary data or archival information that we may have, a conjectural visualization may be done to see how it must have been in ancient times when it was not damaged. So, digital documentation. Now, I will begin with an example of a UNESCO World Heritage Site in New Delhi. This is the Qutub complex in Delhi. So the entire complex has several monuments in various stages of damage. So in the complex, we worked on these 4 structures: the Quwwatul Islam Mosque, the Alai Darwaza, Tomb of Imam Zamin, and the Minar itself. So the terrestrial laser scanner was used here. So the entire workflow was done. So and integration of the data was also done. Point clouds were generated with close range photographs, and damage was detected. Finally, reconstruction was done. So a workflow was developed to overcome the various challenges that we would face in the data acquisition using terrestrial laser scanner and CRP data, that is close range photogrammetry data. Then data was processed. So the integrated data of a framework had to be generated for processing this data and combining it together. Then the alignment of the point clouds from TLS and the photogrammetry images. So now you see, since this is the Minar was a high monument, yes, it had considerable height. So the laser scanner gave us very dense point cloud in the lower parts, but was not so successful in giving us data. There were lots of gaps in the higher stories, the top stories. So lots of gap in the laser scanning data, even though the instrument is capable of giving us very dense point cloud. So missing point clouds, loss of details, and very improper textures were here. So this was a challenge. Now this was overcome. So angular shape, the other aspects were that the angular shapes of the structure. So if you put the scanner maybe here, very proper field planning had to be done. So a very detailed field planning has been done as to where and how many places the scanner has to be put, so that appropriate overlap between scans is properly done. Now there are also complex patterns here, so which obstruct the views. It's not a simple structure. So all these aspects formed very limitations as to how we had to plan the field, right? So this was the field planning for the TLS scan. Now if you see the lower portions have very detailed dense. This is not an image, please note. It is only the point cloud from the laser scan. So the lower portion is quite proper. However, the upper stories have considerable gaps. Now this was compensated by using photographs from the close range photogrammetry technique. So these were done from a near range and from a far range. Again, the proper field planning had to be done. Because near range photograph did not cover the full extent of the Minar, and the photographs from the far range could not cover major parts of the lower portion due to obstructions, because there were trees and other monuments in the line of sight. So to avoid occlusions, the camera stations had to be placed far away. Now, if multiple images are stitched, then distortions were observed. So all these challenges had to be addressed, and one had to take care of this so that the augmented 3D model could be generated. So after proper field planning, we were able to see that we were able to analyze that certain locations would be done from a far range, and the detailed photographs had to be, for detailed 3D models, the detail to be extracted had to be done from a near range. Now here are the results of the integration of the CRP data and the laser scanner data. This is the far range, near range images. These are two image related models, and this is the laser scan. Now, after integration of all of the three data types, you are now able to see that the integrated 3D models gives us a comprehensive, detailed model with enough point density to see even after documentation of this, we would be able to extract even the minute cracks or broken parts, etc., as we will show you in the next section. So if you see here, look at the gaps that are there. Right now, after integration, all the gaps have been filled up, and we see a detailed structure. So these were, similarly, we have done it for other sites as well. After the 3D model has been generated, architectural elements can be extracted. So here what we do is we work with a sample that is available to us. Right? Now, with historical data and from literature, one was able to identify the types of arches in that period of the Sultanate period. And if you see one, you will be able to see which kind of arch would be most suitable. So by studying the angles and other things, one was able to do. We made architectural elements for arches and for domes. So the primitive formation was done, then shapes were fitted and dimensions were estimated for these two structures. Okay. So it was decided that this sample arch would fit the structures that we had at hand most appropriately. So a fitting algorithm was developed and shapes were extracted. And then dimensions were estimated. So all these were taken as samples. These were data collected from the field, and this was the data from the literature. So this algorithm was built up from the TLS point clouds. Horizontal sections were taken. Each small detail was fit in with vertical primitives and horizontal primitives, and then they were integrated along the cross section. Then radius, length, etc. was calculated, and a simplified shape fitting algorithm was done, and then dimensions were estimated. Similarly, a similar approach was done for dome-like structures. So again, from literature, sample structures were identified. The type of dome which most nearly fitted the structure in the site was identified, and a similar approach. So this is this type of dome, this one is this dome. Right? And then again, coordinate structural geometry was fitted. They were sliced. Cross sections were extracted at regular increments along the z-axis and at regular angles radially. Primitives were formed along each cross sections, as you can see, both this way and this way. And then a simplified shape denoting a hemisphere was obtained, and it was then refined to fit the exact structure precisely. Now you see this is the point cloud. So this is the inner view, and after that measurements were taken so that to see how properly had it been extracted. So the radius and the circumference, etc., were calculated and validated with field measurements, and also compared with data in literature from the published data by ASI and other authentic historical sources. So these primitives then can be used for further analysis or can be kept in a digital library and then used later for reconstruction, damage assessment, or then the next part of the documentation would be digital blueprinting. So after these primitives have been extracted, they can be used for digital blueprinting. Now, blueprinting here would be very important because they would form detailed maps of the entire heritage structures or the heritage complex, because for such ancient monuments, these maps would not be available, unlike recent structures like bridges and other buildings. In case of damage, we would be able to use this digital data or digital blueprint for damage reconstruction, etc. So as you can see, each the entire structure is divided into small parts, each primitive, and each element is then extracted by image processing methods. So edge extraction has been done here to get the first primitive for different kinds of structures. So you can see that even the very detailed carvings on the tomb we have been able to extract them with the high resolution laser scanner data combined with high resolution images and applying image processing techniques to them. So the edited and refined shape primitive would be like this, and With that, the dome was extracted separately, and then the jalis were extracted, the patterns of the jali, and on the parapet, different types of carvings are there. The top spire of the dome, pillars, etc. They have all been done separately. First, primitives were extracted, like the example shown in the previous slide, and then they were all done individually. Later, combined, this is the point cloud. The interior was also mapped similarly, and this is the exterior. So this is the front elevation with very, very precise measurements also available. So if on this model we make measurements, we will be able to get very precise measurements, very accurate measurements. So the final integrated blueprint of this tomb of Imam Zamin in the Qutub complex area. Similarly, digital blueprints were generated for Qutub Minar, the first floor, and the front gate here. This is the gate, which has been blueprinted here. Small parts, just to show you that each carving can also be done, and carvings on the front gate. So just to highlight that even very small, minute portions can be very precisely extracted digitally and archived in the digital format. This is another example of a different study area, which we began as a case study. This is a church of the British period in Uttarakhand. And again, similar methodology was applied. For the interior and exterior scans were taken, photographs were taken, data was integrated, and detailed floor plans, front elevation, the back elevation, the left view has been taken, and detailed blueprinting has been done with very precise measurements that can also be taken. And these are digital prints, maps, so that they can be used, modified, or used for planning and monitoring purposes. Similarly, another approach was applied for a slightly different approach was done for multi-scale hierarchical documentation. Now here, the data was unrolled, the point cloud was unrolled and then rescaled to different pixel sizes, and at each pixel size, it was stored in the archive as hierarchical data set. So the purpose of this was that if it was a big damage, that is a large crack, a major crack, this could be used at a certain scale. And if the crack or the damage was very minute, then only a small tile would have to be used. So one need not display the entire data. Instead of that, one could use only that particular tile which had the damage, and the user could process data for that section only. So a database which was hierarchical and multi-scale, as you can see at different scales, was generated so that one need not open and process the entire big data at each time. One had to do some processing. Now, we will take a 2-minute gap, and then my colleague, Dr. Poonam S. Tiwari, will be taking up the section on damage detection and reconstruction. A very quick gap, and then we will meet again.
In this session, and in this session, we will be discussing damage detection and reconstruction. So as you have been told earlier also, that using the ground-based systems, we were able to generate the 3D models. And these 3D models with dense point cloud can be used for damage detection and reconstruction. Now, in heritage structures, we encounter damages because of various reasons, and various type of damages are encountered. So as you can see, that there can be various types of structural damages in the cultural heritage, and basically what we are dealing with is built monuments, is the buildings, the monuments in the heritage. So in the there can be broken patterns, because as you already know that in a monument, in a heritage structure, generally there are repeated patterns, and those patterns, the carvings, the features on the monuments, they can be broken because of several reasons. There can be some cracks, minor as well as major, which have developed in the monument buildings. Because of the failure of building material, you can have certain issues, certain problems can be there. Then out of plumb walls. If you remember in yesterday's session, I have discussed about the tilting of Qutub Minar, and how using this three-dimensional model, we were able to measure the amount of tilt in Qutub Minar. The monuments can also show discoloration, vegetative growth, and vandalism, etc. So these are few of the damages which can be observed in the building heritage. So what we have studied here is the broken patterns and cracks. These were the two major damages that are encountered nearly in most of the monuments. So we try to develop a methodology using which in a semi-automated method, the broken patterns and cracks can be identified. And once the broken pattern are identified, we have also developed the methodology using which the broken pattern can be virtually reconstructed also. Okay, so we will talk about this. So for this broken pattern, for detecting the missing patterns, we have utilized the fractal dimensions. Now, fractal dimensions are a feature of image processing, which appear at the same same at different scale. So if you visualize them at a smaller scale, then also the feature is same, the shape is same. When you zoom it, then also the feature is same. So this fractals exhibit similar pattern at increasingly smaller scales, and this property is also called as self-similarity, also known as unfolding similarity or expanding similarity. So if you, I'll give you a very simple example. If you look at the coastline, okay, so if you look at a coastline from a very very small scale map, then also the coastline has a zigzag pattern. When you zoom in into that coastline at a regional level, then also it shows similar type of pattern. You further zoom it, you again see similar type of pattern. So these natural features, they exhibit a lot of self-similarity. Similar thing is there in the trees also. So a tree canopy, a lot of leaves are there. You just go zooming in, and you go on seeing the similar pattern. So that quality of the images, that quality has been utilized for detecting these missing patterns. So as you must be aware that in the patterns, when the patterns are created in a monument, be it the patterns, carving patterns or designs, anything. So there is a similarity. So same pattern, there is an elemental pattern, and that elemental pattern is repeated at a regular interval, so that entire pattern, entire structure is generated. The same thing you must have seen in the previous session when we were when our colleague was discussing about extraction of architectural primitives. And once that architectural primitive has been extracted, that architectural primitive was copied at different scales so as to complete the entire structure. So the similar thing has been done here. What we have done is we have extracted the fractal dimensions of sample and convolution window. So I will show you this. So this was the pattern, and you can see the upper layer. In the upper layer, the carving is complete, whereas in the lower layer, two of them are complete and two of them are broken. So like this, throughout the monuments, we were finding a lot of such type of broken patterns. So what was done is we have identified the smallest element that can be the elementary part. So, and that for that elementary part, the fractal dimensions were calculated. Now, these fractal dimensions were calculated using a convolution window. Convolution window is one which takes a small area of the image, does some operation, then moves ahead, does the same operation on the second area of the image, moves ahead. You can see here that is the black square window. Okay, so using that convolution window, the similar patterns were identified, and the potential sites were detected, which could be used as the element. So once these elements were elemental area. So once this elemental area was identified, the fractal dimension of the elemental area was calculated. For all the elemental areas throughout the image were calculated, and these fractal dimensions were compared with each other. This comparison of fractal dimensions led us to detection of sites which were broken or in which the patterns was missing. Okay, so as you can see here, windows with similar patterns were identified. So these are the windows with similar patterns using the convolution method. And potential sites, the fractal dimensions were compared and the potential sites were identified. Okay, and how these fractal dimensions were compared? There are various parameters of these fractal dimensions. I'm not going into the details of these dimensions. So as you can see, there is a marked difference in the values of capital M, small m, and mu. So for the areas in which the pattern is similar, the values would be similar, whereas wherever the values are different, the pattern would be missing. Okay, so finding the anomalous values, we had tried to find out what are the broken areas. Okay. Similar thing was done here also. As you can see, this was the input image and the elemental pattern that I was discussing. So this was the elemental pattern. Okay, so using that elemental pattern, the subsets were created and fractal analysis was done. Now, fractal analysis was done and the comparison of fractal dimensions, parameters of fractal dimension was carried out, and if the change in there is a change in fractal dimensions, we say that the area is damaged, and if it is not, if the fractal dimensions are similar, we say that the area is not damaged. So you can see the damaged, the classified result showed us what areas are damaged, and yellow depicts what areas are not damaged. Once this, we have identified that these areas are damaged, so virtually what was done is the damaged part of the image was removed from here, and this damaged part was replaced by an undamaged pattern that we have taken as elemental pattern. So elemental pattern was replicated everywhere where the classification shows that it is damaged part. So a virtually reconstructed image was created. Okay. Similarly, here also you can see this was the full pattern Okay, the pattern of a flower we have selected, that this is a complete pattern, and that pattern was the fractal analysis for the complete pattern was carried out. Fractal dimensions were checked, and the classification was done. What all areas are they're damaged or not damaged. The damaged areas were removed from the original image, and they were replaced by the elemental area. Okay, so as the virtually reconstructed image was created. Okay, here what we have done is, in the previous one, the same pattern is there, but the elemental area was the complete flower. Now, because there is a lot of symmetry in the pattern. So what we have done is we have taken 1/4 of that area and tried to rotate it and find out what all areas are damaged and undamaged. Because what we have observed is that in some part, especially in the third damaged area, the entire area was not damaged. Only a very small portion was damaged. So why to change the entire area? So small elemental area was taken. So that also can be done. Now, that was about how we can identify the broken pattern. Then what we have observed is that if there are changes in material, because in one of the site, in the church that I have shown you yesterday, which was built somewhere in 1895. So there were lot many cracks, as you can see in the second image. This is an optical image. Lot of cracks are visible, and during the restoration work, what they have done, they have filled up those cracks with some material, so as to give it structural strength. But this material is different from the original material that was used for construction of the church, construction of the building. So this change of material, we never expected it, but it was picked up by the TLS point cloud. So as you can see here, this change of material has been picked up by the terrestrial laser scanner. So we were able to identify the areas in which the restoration work was carried out, and the material is different from the original material. So that also is one thing that can be taken up using terrestrial laser scanner data. Also, as you can see here, this is the broken part. Broken part also was being picked up by terrestrial laser scanner, and later on I will show you how we can reconstruct this broken part using the intact part in different area. Okay. Now, to identify the cracks of any dimensions, be it smaller cracks, minor cracks, or major cracks, what we have done is we have tried to use the intensity image as well as the depth and the range data also. So RGB image, that is the normal photograph, and the depth data from the terrestrial laser scanning, we were able to generate this depth data. As I was discussing yesterday, that these terrestrial laser beams are very minute. They are very small, and they can penetrate, they can go inside the crack, and from there also some return is coming back to us. So what we are able to get is, from the crack, for that crack area, the depth of the points is more than when the point is coming from the surface, the depth is less. When it is coming from inside the crack, the depth is more. So what we tried to do is we used the RGB image, that is normal photograph, and we did crack detection using automated methods. These are all automated methods. So we did crack detection only using the photograph. What we found is that the crack was getting identified, was getting detected, but along with the crack, lot many other features because were also getting highlighted. Because what is happening in the monument, there are various carvings, there are various patterns written over there. There's some scriptures also written over there. So lot many things are there. So only the photograph cannot be used for automated crack detection. So what we did was we utilized the photograph as well as depth information. So when we combined both of them and then did the crack detection, so only the crack part was getting highlighted, and automatically this was all was done automatically. So this was how the cracks can be identified. Similar study was done for clock tower in Dehradun also. So you can see this is RGB data, this is depth data, and the crack portion was identified. Okay, suppose there is a damage has happened in an area, and because of that damage, some part has broken, something has happened. So if you have the pre-damage and post-damage data, then by comparing the pre-damage and post-damage data, we can detect the broken portion also. If you remember, I have shown you in the Dharohar application that IIRS has developed. So there was one option for co-registration of different point clouds. So you can co-register point clouds of two different dates, one pre-damage and one post-damage, and find out how much is the damaged area. Okay, similar thing was done here. You can see very minute crack was there in the Buddha statue. So that crack also we were able to identify using the image processing methods. Okay. So again, this the same methodology applied on a different area, and this we have applied on different areas so as to check whether the methodology uh, is valid or can be applied for different areas or not. Okay, so the broken part also can be identified by comparing the pre-damage and post-damage data, as I have shown you for one railing, and this again is for one for another area. Okay, so you can see this part was damaged and that damaged portion was identified. So automatically you can understand, you can find out how much damage is there in the monument. So you need not go and zoom into each and every part of the monument and check it. So you run the algorithm and it will identify where are the damages, where are the cracks, where are the broken portions. So all those can be done. So as I have told you yesterday, that virtual reconstruction of the statues we have done, relocation of the statues were done. So similarly, in some portions, in some monuments, what was observed that the some part is damaged, whereas on the other side, because of the symmetry, the actual design is there, and that actual design is intact. So when we have this intact design, so using that intact design, we can remove the damaged section and reconstruct it from the intact area, from the actual area. Okay, so you can see the reconstruction was carried out using the adjoining area. So we cannot, I just want to highlight here that we cannot fix any one methodology for all these structures, for all the areas. As and when the requirement is there, you can change the methodology slightly so that it fits into your area and deals with the problem that you are having in your area of interest. As you can see here, this was a statue in which one part was intact and the other part was broken. So what we have done is virtually we have removed this broken part taken the intact part from the other side, created a mirror replica, mirror image, and then attached it here, integrated it, and this all was for virtual reconstruction. So these all are virtually done. So later on, once virtually they are done, you can later on, if you want to do the restoration work, that also can be done. Now, previous discussion was regarding how the ground-based systems, especially TLS, and can be used for damage detection. The damage detection can also be done using the satellite and UAV data, because if you want to do a damage detection in a larger area, or instantaneous damage detection you want to do just after the calamity has happened, then the satellite images, the UAV data can be very, very helpful. So if you remember, there was a very big earthquake in Kathmandu in 2015. So and that happened, and the entire area of the entire Bhaktapur area was means lot of buildings were damaged in that particular earthquake. So as you can see here, the first image. The first image is the intact image, when the pre-disaster image, pre-earthquake image taken on October 25th, 2014. And later on, after the earthquake has happened on April 27, 2015, the image has been captured. And you can see that these structures, the tower, this all area has been damaged. You can see in the second image also, I have highlighted it with the yellow circles. You can see the Vatsala Durga temple, that all got damaged. So this plaza in front of Royal Palace of Bhaktapur Kingdom, it is also a UNESCO World Heritage Site. So some study we have done using only the satellite images, how this is Dharhara Tower, which also got collapsed. Only the base got, means the earthquake was very extensive, 7.8 was the magnitude. So what we did was we utilized these satellite images and applied the image processing operations. Because when what happens when in case of such disasters, such as earthquake, the time is of utmost importance. You want to know exactly where the damage has happened. You don't have time for visualization of the image, means you don't have that much time. So what can be done is, because of this international charter gets activated, and the data is freely available, data for the disaster site is freely available to everyone, to all the, especially to the country that is affected. So once that data is available with us, within, I think, a few hours, the data gets available. So once the data is available, what we can do is we can apply automated image processing methods and find out where exactly the major damage has happened. Once we have identified that, we can concentrate our rescue operations into that area. So even though such type of methodology that is developed, that can be useful for heritage monuments, that can also be used for disaster mitigation and rapid damage assessment. Okay, so as you can see here, we have utilized the image textures for earthquake related damage assessment. And please, just for your information, applying these texture measures, calculating GLCM parameters, it is just by a click of button in the image processing software. So once you put the image, click on that, you can generate these texture measures, GLCM parameters. So as you can see here, this was the first image. If you see, This was the pre-disaster, and this is the post-disaster image. In the pre-disaster, this building has a sloping roof, so the boundary of the roof is clearly seen, whereas in the post-disaster, the entire boundary, everything is gone. So if you have such type of data, just by simple comparison, you can the software itself will tell you that these are the areas which have changed, and you can focus your relief work in such areas. So there are other GLCM parameters which can be used for damage assessment. Okay, so there are various applications are there. Now here you can see that was done using texture parameters. We can also use RGB IHS transforms to find out what are the areas which got damaged. So as you can see here, this was pre-event saturation, intensity, hue, and saturation. RGB we have converted into intensity, hue, and saturation for pre-event and post-event. So in the post-event saturation image, you see that all the buildings that got damaged, they were getting highlighted. Okay, because IHS model preserves color irrespective of the intensity. Similar study was done for rapid damage assessment in Bagan area of Myanmar. Okay, in a violent earthquake measuring 6.8 hit the central Myanmar on 24th August 2016, and because of this earthquake, the 14th century archaeological site of Bagan got severely damaged. And as you can see, I have shown you a ground photograph of a pagoda. So many pagodas. Pagodas are Buddhist site of Buddhist temples, you can say. Okay, so and these were 14th century pagodas. So, and that entire area, this Bagan area, is full of such type of pagodas. So this Sulamani pagoda was one very big pagoda which got damaged in this particular earthquake. As you can see here, the ground photograph shows that the entire front portion of the Sulamani pagoda got damaged. So what we have done is we tried to develop methods for damage assessment, and we utilized pre and post data. Also, what we after the disaster has happened, the UAV flight was taken up in the damaged area to assess the damage. So we had that UAV data also, drone data, and we tried to process and develop methodology on that data also. Now, later on, I will be discussing the UAV data, but at this moment, what I would like to show you is that in the damaged post-event data, you can see that half of the portion is going in the shadow area. So in the satellite image, now that particular area, the shadow portion is means the whatever damage has happened, we cannot be sure about that just by using the satellite image. So other methods are also there. So just a very simple method, what we have done was, because time was very important in that sense. So what we have done, once we receive the data, we have created just a line, transect line from one point to another point, and we have seen how the pixel values are changing. Okay, in the pre-event and post-event, you can see a marked difference, because in post-event, because a lot of material has gone down as rubble, so the reflectance has increased. When the reflectance has increased, you can see the pixel values, they show a very haphazard manner. Okay, so you can identify in one instance that where all the damage has happened. Similarly, we can carry out the classification and change detection. So object-based analysis and change detection was carried out so as to find out how much damage has happened. We also utilize the GLCM texture parameters, utilizing our knowledge from Nepal earthquake time. So we use that knowledge and we apply the GLCM textures, first order and second order, and try to find out how much damage is there. So we found that these textures, GLCM textures, are very, very useful for detecting damage on a larger area. The finer damages such as cracks and broken patterns, for such type of damages, the ground-based instruments were required. So again, you can see we have also used fractals for this and variograms also. Okay, so all the image processing operations we have used and we have utilized and tried to find out using which application, using which algorithm we are able to get better results. Okay, so these are variogram, results of variogram, and it is also able to show us the damage area in both the regions, both in the shadow area as well as in sunlit area. You can see this was the shadow area. In the shadow area also, variogram is able to give us the data, the information. For the same area, we have used the satellite image also. As you can see, this was the first image is satellite ortho image. So as I have already discussed, that some part of the building, some part of the monument is going in the shadow part. Whereas when we use the UAV image, we don't have such issues and the entire area is visible to us for analysis. Okay, so in the satellite image the damages were detected, and in the UAV image the damages were detected. So we found marked improvement in UAV image. Okay, because UAV mounted sensor was a multi-directional view and it enabled clear visualization of damage and debris. So this was the photorealistic 3D model using UAV data. Okay, you can see this is the UAV data. The damaged points were classified, and these are the damaged area. You can see this all in the 3D point cloud. You can see this all is the damaged area. Okay, this is the damaged area. So this is all from my side.